Multivariable calculus, we're back in 15.9, part 2. Just finishing this problem. We had found all the parts, our rho, theta, and phi. So the answer that we would be writing down, of course, would be this. All right, so it's one thing to go from one coordinate system to another. It's entirely different than to turn this into something useful for calculus. And you can see as you look at this box here, I've highlighted in green, as you change from rectangular coordinates to spherical coordinates, what you're going to notice is instead of having a dv with a d x dy dz, you're going to get this change to rho squared sine of phi d rho d theta d phi. And you're probably thinking, okay, where does that really come from? I'm going to show you very quickly. And let's just say that we look at a little cube of volume here, a little cube of volume. And you can see a little wedge right here. We're really going to make use of this arc length formula that you learned back in geotrig. That as long as you're in radians, the radius multiplied to an angle would be an arc length. And personally, I think, the trickiest part is going to be coming up. We might as well talk about that right now. The trickiest part is involving how to get theta into this picture. D theta is down here, a little slice. And, if we were to look at this, remember R really came from a polar kind of a scenario. You learned about polar coordinates back in single variable calc in just the xy plane. Imagine that you lift this slice up, and in red here you've got that r, and then you've got your d theta. Well, what I'm getting at is this. If you wanted to find this component right here, just in yellow, that dimension of that little cube of volume, well, you're going to say r times theta. So one of those dimensions that you're going to have is going to be your r. But remember what we saw with r on the front page of the notes. R, we proved, was always rho times the sine of phi, or sine of phi, I should say. Some people say phi instead of phi. But as you're looking at that, then you could say, well, your r is going to be rho sine of phi, and then you'd have your d theta. So that's one dimension of this box. As you're looking at rho right here, you can extend to d rho. That's how it's changing. So you'd be multiplying by a d rho. And then let's take a look in blue right here. I'm just drawing over that. You can see that phi is going to be changing this much. Now you've got that radius. It's the same arc length formula where rho gets multiplied to this change in the angle, which would be d phi. So you multiply that all together, and what do you get? Well, a rho and a rho is a rho squared, and then you'd have a sine of phi, and then you've got your three differentials, and that's what we've got in green. So I just wanted to make sure you've seen that. Sometimes kids are a bit in shock when they see that, thinking, where in the world or how could that ever come about? It's all getting into little accumulations of volume, like little rectangular boxes here, or approximately rectangular boxes when you get super, super tiny. And that's about what a tiny little volume accumulation would look like. So as we go ahead and take a look at, say, example 3, let's see if we can use what we've just been talking about and maybe get a little bit of help with this. We know that we've got a triple integral that we need to work out. You've got x squared plus y squared plus z squared. You're told that b, where you're going to be integrating over, is this unit ball. This unit ball is a sphere with everything included inside of it. It's like a solid sphere, so to speak. And you'd think, well, gosh, how can I work this out? Well, we know that x squared plus y squared plus z squared is equal to rho squared. We also know that x from our front page was rho sine of phi, cosine of theta. We know that y was rho sine of phi, sine of theta. Pardon me, I said sine of phi and I didn't write that. And then finally, z would be rho cosine of phi. So as we look at this, as we look at that unit ball, we could say, you know what, this x squared plus y squared plus z squared, well, let's immediately see if we can start at least getting a little bit of help here. We're going to have rho squared to the 3 halves with a dv. And, now our integral, or integrand at least, is we, are going to be multiplying powers to powers, 2 times 3 halves. You'd just have rho to the 3rd, right? But then what? If we decide to change this to spherical coordinates, well, we may certainly do that. Just like I said before, now we're going to change our differentials. We're going to have a rho squared sine of phi d rho d theta d phi. Well, let's take a look at rho. We've got a unit ball, and from the origin going out, you can see that rho can only span any point inside of that ball. Will be a distance from 0 to 1 from the origin. As we look at theta, well, theta is going to span all the way around, so we're going to be going between 0 and 2 pi. As we look at phi, well, we're going to go from the top of the positive z-axis all the way down to the negative z-axis. We're going to go between 0 and pi. Now at this point, I do want to call something to your attention. There are a couple of ways we can work this out. We could just go step by step and immediately start working this out. Or just wanted to quickly point out, I believe this was in lesson 15.2, going way back. Yes, as we look right here, you might remember with the double integrals, if you had 2 functions of different variables, a g of x and an h of y, we could just separate that into 2 single integrals with respect to those variables and multiply them together. Unbelievably, we may do the same thing here, and that's very good news. You don't have to do that, but I certainly wanted to make note of that, because this could really clean things up. Let's just look right here and see that we've got 2 functions multiplied together with respect to rho, and our integral goes between 0 and 1. So I'm going to have e to rho cubed times rho squared d rho. And then we can say, well, what about d theta? Well, theta is going to span between 0 and 2 pi. There's nothing left inside the integral, so we could just put a 1 in there. That's kind of nice. How about phi? Well, as we look at phi, we're going to say that goes between 0 and pi, and we'd have the sine of phi d phi. So at this point, we can work this out. It actually turns into really a single variable calculus problem. As we look here, we can note this is like a problem with just a basic u substitution. In fact, a great review. We could say u is equal to rho cubed, and du would be 3 rho squared d rho. D rho would be du over 3 rho squared. And then change your bounds. If you'd let rho equal 0, u would equal 0. If you let rho equal 1, you'd still get a 1. So we do need to make note of that. Of course, we don't want to lose sight of that. The changing of the bounds. Here it's going to appear that we didn't do that at all. But you can see that your p squareds, or rho squareds, I'm so sorry, would cancel out. And you're going to take an antiderivative of e to the u with respect to u. So we'd get a 1/3 e to the u. Evaluate that between 1 and 0. Well, you'd get e to the 1, which is just an e, minus e to the 0, which is just a 1. And you'd say, well, hey, there I go. I've got that working out rather nicely. How about d theta right here? We'd have theta evaluated between 2 pi and 0. I think you could see it's 2 pi minus 0, which is just going to be a 2 pi. As we work this one out, this might be the one that's going to take the most amount of work here. Well, I don't know. I guess our first one had the substitution. But you can see our antiderivative is negative cosine of phi. As we plug in, we'd get a cosine of pi minus the cosine of 0. And this would be negative 1 minus a 1. That's negative 2. And multiply by a negative, and you'll just have a 2 right there. So a 2 times a 2 pi is a 4 pi. So we could say we'll have a 4 pi over 3 with this e minus 1. And look at that. We have our final answer, and we were able to work that out rather nicely. All right, there is one more problem, and sadly I don't think we're going to be able to finish it. I'm going to change the directions a little bit right here. For example, for u spherical coordinates, to write an integral, how about a triple integral, representing the volume. So we're going to change that. We won't get a final answer per se. We just want to write the integral that would represent that. So we're going to have a cone. Z equals the square root of x squared plus y squared. I think we all can agree that we'll have the origin 0, 0, 0 there. And then, of course, z is positive, so it's a cone that's going to be opening upwards. And then we've got this sphere. And the sphere is actually going to be right on top of the cone, and it's going to almost look like an ice cream that goes on top of the cone. But let's see what would happen here. I've graphed that off to the side, but I just want to do a little bit of work. We're going to have to complete the square actually to find out what's happening. I'm going to minus a z right here, and completing the square, we always would take our linear term, that negative 1, and we're going to square it, or take half of it, pardon me. We always take half of that middle term, and then we square it, and we'll get a 1/4. So we're going to add a 1/4 to both sides, and we'll have x squared plus y squared. And actually, what you take half of, that half of negative 1, a lot of teachers even say put a star by it, because that is honestly the term that you have in the perfect square. And you can see very quickly, this is what you're going to have, a center at 0, 0, 1/2. The right side is r squared, your radius is 1/2. So if you were to go 0, 0, 1/2 and come up here, this would be your center, and then you'll rise up 1/2 all the way. So this is really what we'd get, this cone on the bottom, and the sphere is going to be up on top. We're running out of time. We'll work out the integral next